So yeah, so basically, with my y equals sine x graph, it should look like this, okay? That would ordinarily be 90 degrees, which is pi over 2 radians. That's 180 degrees, which is pi radians. That's 270 degrees, which is 3 over 2 pi radians. And that is 360 degrees, which is 2 pi radians. And then you're happy it's just going to repeat again and again and again in both directions. You all happy with that? Okay. What would the height of this graph be? What would the maximum point of this graph be?
1.
Perfect. And what would the minimum be?
-1.
Negative 1. Now, if you're not sure where this comes from, I think I have a video on there which describes it. Okay? It literally just comes from thinking about the unit circle and thinking about trigonometry to do with the unit circle. If there's not one there yet, there soon will be. Okay, there soon will be, because I'm doing it with my other class. Okay? But anyway, if you just take away from this discussion, that is the graph y equals sine x, and if you have some understanding of what radians and degrees are, that's all good. Okay. Now, going from where I wanted to go, okay, I want to work out what the derivative of this graph is. So in other words, I want to work out what is the derivative of sine x. Boys, can I have a bit of quiet, please? Thank you. I want to work out what is the derivative of sine x. Now, if I'm differentiating, what am I literally finding? If I differentiate something, what am I literally finding? The gradient. Good, so you know the answer. Good, I'm literally finding the gradient or the rate of change. Okay. So all I need to do is think about this graph. I'm going to make a copy down here. And this graph is going to represent the derivative of this graph. So watch this. Okay, I'm first of all going to consider each of my points. This is going to be pi by 2. This will be pi. This will be 3 pi by 2. And this will be 2 pi. Okay, so can you see I'm just literally matching up my x values down here? Okay. So what I'm now going to do is I'm going to consider what my gradient is doing at each individual point. Okay, so have a look. At this point here, are you happy that my gradient is at a maximum? Yep. Okay, so when I come down here, remember this is my gradient graph. Down here, my gradient should be a maximum. It should be a positive value. So I'm just going to draw that there. Okay.
Can I ask why is maximum position? Gradient?
Look at it. At that point there, you're happy my gradient, my tangent, has a positive gradient.
Yeah.
Yeah? And it's a maximum over here, because as I move over here, it's going to be less positive. As I move over here, it's going to be less positive.
Okay.
Make sense? Okay. What about a pi by 2? So at that point there, what's the value of my gradient?
Like 0?
It's going to be 0. So pi by 2, the value of my gradient is 0. You happy? So these dots represent what my value of my gradient is. Okay. What about a pi? What's my gradient doing? Careful.
1. No.
There's a slope. So it's going to be negative, and it's a maximum at negative. Or minimum, rather. Okay, so there you go. Okay. All right, what about 3 pi by 2? What's my gradient doing? It's going to be 0 again.
0.
Okay. What about 2 pi? What's my gradient? Yeah, good, positive. So I'm going to draw it up here. Okay. Now, all I'm going to do is just join together these dots, which I've made. Okay. Now, have a think. Am I going to join these dots together with a straight line?
No.
That doesn't make sense, because have a look at my curve. Okay. It kind of grows really quickly there, and then it grows less quickly. So the rate of change is not constant. Okay. So in other words, I'm going to join them together with a curved line. Okay. So here we go. So I'm going to join them together with a curved line. And I get that graph. What graph is that?
Cosine?
It's cosine graph. So what I can say then, really interestingly, what I can say is that the rate of change of sine x is exactly equal to the cosine x graph. Okay? So in other words, when I differentiate sine, I get cos. Okay? Can you have a go then at differentiating this graph? Can you have a go at differentiating cos x? So literally exactly the same process I did before. Shall we quickly do it? So at 0, what's the value of my gradient for cos x? 0, right? Okay. What about at pi over 2? What's the value of my gradient?
-1.
Yeah, good, it's negative. Okay, what about pi?
0.
So 0. What about 3 pi by 2?
1.
Yeah, it's 1, it's positive. Good. And what about 2 pi?
0.
It's 0 again. Okay, so now I just connect together my dots. So here we go. Let me get that graph there. Okay. Now have a look. What does that graph look like?
Minus sin x.
Yeah, if you have a look at sin x, all that's literally done is all the positive values have become negative, so that's flipped over down there, and all of these negative values have now become positive. Do you see that?
Yes.
Yes, so all of these positive values become negative, and all of these negative values have now become positive. So therefore, this thing is just the negative of sin x. Okay? So in other words, the derivative of cos becomes negative sine. Okay? And in fact, you can carry on going like this for negative sine and negative cos. But what you will notice, if I clear some space, what you will notice is this pattern here. So if you start with sin x, if you differentiate that, what did we say we got? Yeah, the cosine of x. And if you differentiate cos x, what did we get? Negative sine x. So can anybody think what would we get if we differentiated the negative sign? Negative cos. Can you see that? Because sine, negative sine, cos, negative cos. If we differentiate negative cos, what should we get? Back to sine again. Okay. So in fact, this is different to what we were looking at last lesson. Okay. So far we've been looking at functions like this. So y equals x cubed, or y equals x squared plus 4x plus 2, for example. Okay. So these types of functions are called polynomial functions. They're called polynomial functions, right? In other words, if you differentiate these functions, eventually they will go to 0. Okay? If you differentiate polynomial functions, eventually they will go to 0. Yeah? Have a look at this one. If you differentiate this, what do you get? Okay, and then if you differentiate again, what do you get? And then if you differentiate again, third time, what do you get? 0. Okay, so eventually with any polynomial function, if you keep differentiating it enough times, it will always go to 0. But have a look. With this type of function, so these are trigonometric functions, it doesn't matter how many times you differentiate them, they're just going round and round and round in a circle. Okay? So you can say that these are infinitely differentiable. Infinitely differentiable, because you can differentiate them an infinite number of times. Okay? You can also call them cyclic differentiable.
I wonder if anyone tried to debunk that.
Why? Why would you want to debunk it? I've just proved it to you.
No, if they tried, like, I don't know, some crazy mathematician did, and I'm going to do it, so.
Yeah. I mean, you could always try and debunk it.
I'm not.
Okay. Fine. But these are cyclic differentiable because you can just differentiate them and they just go round and round and round and round as many times as you like. Okay? Good. So if I asked you then to differentiate negative sine x, what would that be equal to? What derivative of sine x be equal? Negative sine x be equal to? What's the derivative of negative sine x? It's negative cos x. Does that make sense? Because you're here, differentiate it, you go to here. Okay? What would the second derivative of negative sine x be? Yeah, so you're here, you go to here. What would the third derivative of sine x be? What did you say? Good. And what would the fourth derivative be? And then we're back to the beginning again. Okay? Does that make sense to everyone? So how you differentiate trigonometric functions. Okay. Now I suppose a good question would be, this is fine, so we know how to differentiate sine or cos, or the negative of those, but what if we wanted to differentiate like tan x? That's not on here. We can do it, but not yet. We will get there. And we'll get there on Thursday, whenever I next see you. Okay? So for the moment, store this, think about this for a little bit, okay? We will revisit this again on Thursday, But just for the final 20 minutes or so, okay, can I ask you, well, in fact, no, we'll go through it together. We'll go through this together. So can I ask you, just while I'm rubbing the board off, for 2 minutes, can you just talk about something completely different? Okay? So think about something different from like differentiating trigonometric functions.